Okay, Applied Physics, homework 74. First, I'd like to take this opportunity to wish happy birthday to Regina. Happy birthday, Regina. Now, homework 74. Torque. Torque, here's the formula. Torque is mass times torque arm. Here we have the fulcrum, 8 pounds. There's a fulcrum line. Here's the question. Your goal is to get the stick above into rotational equilibrium, and that's when the torque on each side is equal, causing the stick to be balanced. We've done it in class. Compare the weight needed at B to the weight at A to achieve rotational equilibrium. So this is more theoretical. You don't really do a lot of calculations here. But the idea is that the torque arm here is shorter than it is at B. And if this is 8 pounds, therefore the weight to make them balance would need to be less than 8 pounds. Okay? Less than 8 pounds. So you could say the and you should write it in complete sentences, please. I'm going to save some time and not do that. Weight required at B will be less than 8 pounds, or less than the weight that's at A, something like that. Okay? This one, drawing the fulcrum at the proper location in order for the stick above to be in rotational equilibrium, centimeter measurements on stick are drawn to scale. Okay, so it doesn't really require math. It says use your calculator. I think that's difficult to do that. The idea here is that this is 100 pounds and this is 25 pounds. So this is 4 times more weight than this. Therefore, for it to be equal, the torque arm here needs to be 4 times longer than the torque arm here. Okay? And that's the thought here. Now, how to do that? Well, there's a few ways to do it. Some people could just trial and error it, and maybe you would try. Let's say you would trial it. It's not great, but let's just see if I think it's here, let's say. Now I have, this torque arm is 1 centimeter, basically, 1 centimeter. So, therefore, if that was the case, I would want the torque arm here to be 4 times that. So it would be 1, 2, 3, 4, and the weight would be here, but that's not the case. So it can't be there. So what you're going to end up with, and if you didn't really get there, just please understand it once I show it to you. The answer is this. Your fulcrum would be right at 6. Because therefore what you have is, this here is 2 centimeters. That's what that is, okay? And therefore, what you should have then is, you want this to be 4 times that. So this should be 8 centimeters, which it is. 2, 4, 6, 8. So this is, right, or 6 to 14. This is 8 centimeters. And you always can go back and check. You always can go back and check. And then this would be 2 centimeters times 100. That would be 200 centimeters pounds. And then this would be 8 times 25. That also would be 200 centimeter pounds. And those are equal. It would be balanced. Okay. Next page. So here we go. Here we have this wrench on a nut. You have 60 pounds of force pulling up. This torque arm in this case is 2.3 feet. Calculate the torque applied to the nut when the wrench is pulled upward as shown. Include proper units. So what you do from the formula on the front, torque equals 60 pounds. That's kind of the mass or the force times 2.3 feet. Let's glurf the units for sure. Pounds times feet. So that's where you get your foot pounds of torque that we talked about. And then you get 60 times 2.3. That's going to give you, I think it's 138. 60 times 2.3. 138 equals 138. And again, foot pounds is what you usually say. Foot pounds, okay, of torque. That's what's applied in this case. Now this also applies to this. If the nut is stuck and requires 170 foot-pounds of torque to loosen it, will the person applying the force to the wrench successfully loosen the nut? Well, we figured out 60 pounds of force, it gives you this much torque, 138 foot-pounds, but I'm telling you that it requires 170 foot-pounds, so it's not enough to loosen it, so the answer is going to be no, they'll be unsuccessful. they need to apply more force, or perhaps like we showed, extend this wrench or get a larger wrench to increase your torque arm to get more torque on that nut to loosen it. Here we go, 5. Pretty awesome bag of flour. It's 80 pounds. Here's the fulcrum here. I have 700-pound weight here, so this shows how you can lift really heavy weight off the ground. 700 pounds, 1.2 feet, and we know our bag of flour is 80 pounds. Calculate the distance from the fulcrum, which is also the same as which is going to be the torque arm distance from the fulcrum. You would need to place a sack of flour in order to lift it 700 pounds. So to lift it, it would have to be the torque on this side going down to be equal to the torque produced by this right here. So the torque on this side is 700 pounds times 1.2 feet would equal the 80-pound sack of flour times, sort of X feet. We don't know how far that's going to be. So 700 times 1.2 equals 840. And make sure you put the units on 840 foot-pounds, or pounds-foot, whatever you want to say, foot-pounds. And you could just do it like this if you'd like. Equals, again, 80 pounds times X feet. Okay, you do this to the 80 pounds, cancel each other out. So divide this by 80 pounds. Please, let's do units first. What's going to happen? Pounds and pounds will cancel out. I'm left with feet. Therefore, 840 divided by 80, well, I had 840, divided by 80 equals 10.5. It's going to be feet. Answer, 10.5 feet is where you place that 80 pounds. So I like the idea of you can lift 700 pounds with 80 pounds as long as your torque arm here is enough of your lever. Really cool. We did it in class. I like it. Here we go. How are we doing on time? Fred wishes to lift a heavy crate using the lever setup shown above. Right, 110-pound crate, kind of like we did in class. Explain the relationship between how far from the fulcrum he applies the force and how easy it is to lift the crate. Complete sentences, please. So, explain how far from the fulcrum now B doesn't apply to this. B applies to part 2. So he has a choice to apply weight here, anywhere along this. The relationship between how far from the fulcrum he applies the force and how easy it is to lift the crate. You want to say the further he goes to from the fulcrum, the easier it will be for him to lift the weight. Or you could say the closer he is to the fulcrum, the more difficult it will be for him to lift the weight. And we saw that when we did it in class. We had this setup basically, and you pushed down here, and you pushed here, and you pushed here, and you saw it was way easier to lift it here than it was closer. So that you want to write that idea right there. That's key. Here we go, same picture. Fred decides to push down on the lever at B. So that's where he's going to push. That's his spot. Okay, his torque arm is going to be this in this case. But if the fulcrum is moved toward B, how will this affect the amount of force necessary for Fred to lift the crate? Complete sentences, please. So in this case, if the fulcrum is moved this way, let's say I now move it in here. This is the new fulcrum, this is gone. Now this is my torque arm here, and this torque arm just got shorter. How is this going to affect the amount of force necessary? It's going to, moving the fulcrum closer this way, it's going to cause more, he's going to have to put more force here to lift that crate, because this torque arm is getting shorter, his torque arm is getting shorter, and the torque arm here is getting longer. Okay? So you want to explain that. 8. Check this out. So there's multiple choice 1 through 6. The setup above is in rotational equilibrium, meaning that it's balanced. Distance n must be. So check this out. If this is 500 pounds, and I don't have any numbers here, it's not the scale, 500 pounds, and n is 100 pounds. Okay, what must n be compared to m? N be compared to m. So, this is 5 times 100 pounds. That's the idea here. Therefore, for it to be equal, this distance must be 5 times as much as m. Okay? So if this is 1 foot, let's say, this would have to be 5 feet. And you could do this as an example, and then I would do 5 feet times 100 pounds gives me 500 foot-pounds. Right? And then here, 500 pounds times 1 foot would also give me 500 foot-pounds, and then that would be equal. Therefore, the answer should be 4. This one. So hopefully you understand that concept. It's about the concept. It's about the concepts here. This does not require calculators for this. As this is the same thing here with X and Y. I have two setups. Excuse me, not to scale. Key not to scale. 900 pounds, 900 pounds. Notice where the fulcrum is here. Okay. This, and in Y you have a longer torque arm on this side for the 900 pounds, shorter torque arm here. Okay. Without doing any math, which lever setup would it be most difficult to lift the heavy weight? Most difficult, meaning the most force needs to be applied here or here. And it would be Y. Because here, this is a longer torque arm here, makes the total torque here more than the torque here. And also, this is now less here, so this force produces less torque because the torque arm is less. Okay? This would be easier because this is shorter and this is longer. And this would be more difficult because this torque arm is shorter and this is longer. Answer, what most difficult, it would be Y. So, we're going to have a quiz on this, so come see me ahead of time, not 3 minutes before class, but it's going to be stuff like this, not these exact questions, but similar idea, concepts, and maybe a calculation or two on there using the calculator. But good luck. If you have questions, again, like I said, come see me. Watch this video a few times. Watch 71. Video 71 also deals with this, and that would be good help out. Everyone wants you to do well on this quiz. Mr. Gazda signing off for homework 74.